Good morning and welcome to my presentation on seawater intrusion in coastal aquifers. Seawater intrusion is the movement of saline water into freshwater aquifers, leading to salinisation. This does occur naturally to some degree, for example the breakdown of natural barriers, but has been intensified by human activities such as excessive extraction of groundwater and climate change impacts such as increased storms and rising sea levels. Approximately 70% of the world's population lives in coastal areas, and the majority of these people depend on coastal aquifers for fresh water, and therefore it is an important resource for urban, agricultural, and industrial activities. Increased saltwater intrusion can also lead to the loss of freshwater vegetation and the spread of saline flats into previously vegetated areas, which can lead to a decrease in the diversity of flora and fauna of an area. In Australia, continuing population expansion and a significant reduction in rainfall has led to an increasing dependence on coastal groundwater resources. The reduction in rainfall means that there is a low recharge of coastal freshwater aquifers, which can lead to an encroachment of seawater. Currently in Australia, seawater intrusion has only been noted in a few hotspots, such as the Kwinana industrial area of Western Australia. But there are concerns of significant irreversible damage in many more low-lying coastal landscapes. This image demonstrates seawater intrusion in a natural manner. Under normal conditions, freshwater flows from inland aquifers and recharge areas to coastal discharge areas to the sea. This natural movement of fresh water towards the sea prevents saltwater from entering the freshwater coastal aquifers. This interface is the diffuse zone where the freshwater and saltwater mix and is referred to as the zone of dispersion. Also, because freshwater is less dense than saltwater, it floats on top. As a result, saltwater can be pushed inland beneath the freshwater. Due to high population growth and industrial developments, groundwater has been exploited. The intensive extraction of groundwater from coastal aquifers reduces freshwater outflow to the sea and creates local water table depression, causing seawater to migrate inland and rising towards the well, resulting in a deterioration in groundwater quality and salinisation. When there is more fresh water being pumped from the ground than groundwater can supply, which is often seen in densely populated coastal areas, the well starts to pump with an increased salt content. This salinisation can render the groundwater unusable when freshwater is mixed with about 3% of salt water, and in some cases, less than 1% can see the water unfit for drinking. In addition to excessive groundwater pumping, rising sea levels could accelerate the landward intrusion of seawater. Climate change impacts such as sea level rise and precipitation variation that affect recharge rates are influential climatic factors that affect seawater intrusion. Warming global temperatures will result in the thermal expansion of the world's oceans. In combination with glacier melting, will result in a rise in sea levels. The fifth assessment report of the Intergovernmental Panel on Climate Change points out that sea levels will continue to rise by between 0.26 meters and 0.82 meters by 2100 in the worst case. With this, coastal communities will be faced with an intensified saltwater intrusion and potential water shortages. In image A below, it shows the location of the saltwater-freshwater interface under normal conditions. And in image B, the scenario of sea level rise, which allows seawater to intrude into the aquifer and contaminate the coastal well. Climate change is likely to also cause an increase in both frequency and intensity of extreme weather events. Combined with sea level rising, this change is expected to lead to saltwater flooding in the areas of coastal wells. Wells could be subject to both inundation and physical damage by the storm. The duration of such inundation would likely be brief in the event of storm surge, and the risk of saltwater contamination would therefore likely be short-lived. Heavy precipitation is another extreme weather event with a potential impact on aquifer recharge. If total amounts of precipitation remain relatively unchanged, yet come in fewer but more intense events, one possibility is that a higher proportion could be lost in the form of runoff rather than being absorbed into the ground. This could result in reduced aquifer recharge. Saltwater intrusion is occurring globally, especially in coastal areas of arid and semi-arid countries, where the conditions are drier, populations denser, and these communities rely heavily on groundwater for drinking and agriculture. One significant area where this is occurring is in Egypt. Groundwater is the second main source of water after the River Nile in Egypt. Numerous aquifer systems exist, and it is one of the largest groundwater reservoirs in the world. However, the aquifer is subjected to severe seawater intrusion. This is due to a variety of reasons, the main which being rising sea levels of the Mediterranean Sea, limited natural recharge, and overexploitation of the aquifer due to the massive population increase. Investigations have found that seawater intrusion in the Nile Delta aquifer has extended inland more than 100 kilometres from the Mediterranean coast. In a study conducted by Sefel Nassar and Sharif in 2013, it was found that up to 32% of the total area of the Nile Delta will be submerged under the 1 metre sea level rise. 1/3 of the groundwater resources will be lost, and the available volume of fresh water will be reduced by about 15%, assuming that the current pumping rates will be maintained. Reducing the groundwater pumping by about 50% would most likely sustain the freshwater resources under the condition of a 0.5 metre seawater rise. Simulated models have been developed which should be utilised in the decision-making process to compare groundwater extraction plans to make informed decisions on how to best proceed. In a study conducted in the area, SWI Code, which is a computer program designed to simulate three-dimensional variable density groundwater flow, was used to study groundwater flow and seawater intrusion and how it can best be controlled. Controls included decreasing abstraction, increasing recharge, and abstracting brackish water. It was found that individually, the abstraction of brackish water gave the higher reduction of seawater intrusion, but a combination of all three scenarios have the highest reduction in seawater intrusion. Seawater intrusion is not as widespread in Australia, although it is being seen in some coastal areas. One area which has experienced this is the Kwinana industrial area in Western Australia. Due to dry conditions, there has been a gradual falling in groundwater levels, combined with heavy extraction of groundwater for industrial use. Currently, 58% of water used by industry is groundwater. Tests have shown that salinity levels in freshwater bores along the coast are increasing, and in some areas, the seawater interface has pushed up to 1 kilometre inland. The area contains a number of high conservation value wetlands, and therefore it is imperative that these wetlands are protected from seawater intrusion. The Cockburn Groundwater Area Management Plan was initiated in 2007 and evaluated periodically over time. In 2008, it was superseded by the Cockburn Groundwater Allocation Plan. The plan details the approach to regulating and managing the extraction of groundwater in the area. Key points include that previous allocations set cannot be sustained. New allocation limits are set as resources are already over allocated. And it also supports the use of new and existing alternative water sources to meet the future demands, such as the reuse of treated wastewater and managed aquifer recharge. The key to management is prevention, because once a bore or aquifer has become encroached with seawater, there is little to be done to reverse this. Therefore, managing human activities is essential to sustain groundwater supplies. This can be achieved through setting water allocations and the reuse of treated wastewater. A water allocation plan should be put in place to outline how much water can be extracted from groundwater resources, while also ensuring the longevity of the resource. Key elements of a water allocation plan should include setting rules for water trading and the buying and selling of water licenses, and to set annual allocations. You should also determine how water is to be shared amongst the different types of license users by setting the priority of the supply. Also sets monitoring and reporting requirements and provides planned environment water. Another management technique is the reuse of treated wastewater. Wastewater is a used water from households and businesses that is disposed of through sewage networks. After this wastewater has passed through the treatment process, it can provide a sustainable source of water. This wastewater can then be injected into aquifers. This is called managed aquifer recharge. The benefits of managed aquifer recharge include generation of additional water supplies that would otherwise be wasted. It reduces potential for saltwater intrusion. It stores recharged water to meet demands. And it also increases water availability for commercial and environmental uses. Thank you very much for listening to my talk on saltwater intrusion. It's always best to remember that when we are moving forward with any management plan, to ensure that you are including stakeholders from the start all the way to the end. So these stakeholders would include the local community, and this can be done through community talks and consultation nights. Also dealing with industry and local farmers, and government bodies from local, state and federal. Thank you.